Assalamu alaikum. We know when electric current passes through a coil or inductor, the self-inductance of the inductor opposes the flow of a current. To establish current in the inductor or coil, some work has to be done by external agencies. This work done stores in the inductor in the form of magnetic potential energy. So in this video we will get the expression for energy stored in an inductor. For that I assume that the inductor is free from any resistance and the induced EMF in it can be obtained using Faraday's law of electromagnetic induction. According to that, EMF induced in a coil is equal to rate of change of magnetic flux linked with it. Here phi B is nothing but magnetic flux. And we also know that the magnetic flux is directly proportional to the current flowing through it. If it is so, when I remove proportionality, I get a constant. I need to include a constant along with equal to sign. I will remain here as such. Now in the place of this constant, I use L. Okay, L is a constant here, which is nothing but self-inductance of the coil or inductor we have used. So if I substitute this, I take this one equation number 1, this has equation number 2. I substitute 2 in 1. So what I get if I do so? Then I get a new expression for EMF. Then I have represented EMF by letter epsilon. This one is a epsilon. It represents the EMF induced in the coil. So as such, in the place of phi B, I write Li. Here, L is a constant, so it is taken out. 1 minus L is taken out. So what remains here is nothing but d upon dt. Next, there is opposition to the flow of current, isn't it, in the inductor. To overcome that, some work has to be done. The work done by us to establish current in the coil is taken as dW, and it is found to be equal to the product of EMF and the charge dq. Okay, what does it mean? It represents the work done to make a charge dq to flow in the coil for a time of t, dt. Okay, so the work done to make this amount of charge to flow in the coil. This is what it means. We know the value of epsilon is given here. I name this equation as equation number 3 for my convenience, and this one is 4. Now I am going to substitute 3 in 4. So if I do so, what I will get? I get the value of dW to be equal to, already I have minus in here, and one more minus in from equation number 3, minus L di upon dt. It is multiplied with dq. Okay, now I rearrange it in this manner. What I do, see, dW, there minus on multiplication of this minus sign becomes plus. So what remains is this L. I take a di and write it here, then dq upon dt is written in this manner. We know current, electric current I is nothing but rate of flow of charges through a conductor. So I is a dq upon dt. In the place of this, I can write I. Clear? So dw, which is the work done to establish current in the coil, is equal to L multiplied by di, and here what you get is I. Now I rearrange this and write it this manner. dw equals to L I di. So I box this and I name this one as equation number 5. Now if I integrate the equation 5, I will get the total work done to establish current in the coil. Okay. On integration. If I integrate this, what I'll get? I'll get this. Integral of dw. If I integrate dw, I'll get w. How? We know integral of dx is equal to x. In a similar way, integral of dw will be w. Okay, total work done is equal to the remaining term. Integral of Li di. Here L is constant, so it is taken out. What remains here is nothing but this integral of I di. Now, when I integrate, just remember this. There is one more equation I am going to introduce here. Suppose I have integral of x dx. Then on integration, we get x square divided by 2. The similar way, here I have integral of I di. When I integrate this, I will get I square divided by 2. Now here, I provide limits to this. Lower limit is 0 and upper limit is I. The lower value of current, and this is the maximum value of current. Okay, it's I. So what I get here? L I square divided by 2 on the integration. Now write the values outside. Lower limit and upper limit. Then now in the place of I am going to substitute the upper limit and lower limit. If I do so, what I'll get? I'll get this W. Here, the work done by the external agency to establish current in the coil is stored here in the form of magnetic potential energy, and it is represented as U B, capital U or B. Clear? I just want to be go to L when I substitute the upper limit. This I square divided by 2. Then in the place of I substitute 0. So 0 square is 0 divided by 2. So again 0. What I get is this equals to L I square divided by 2. If you divide 0 divided by 2 is nothing but 0. So what you get is nothing but this. UB equals to half Li square. This is the final expression which gives us the energy stored in a coil or inductor. No? When electric current flows through it. Fine. I named this one as equation number 6. Now, next, there is one thing called as energy density. We call it energy density, which is represented by letter small ub. Energy density. Energy density is represented by letter small ub. Energy density is nothing but the energy stored in the coil per unit volume. Energy stored per unit volume is referred as energy density, and it has got symbol small ub, whereas energy stored is represented by letter capital UB. No? Now I am going to substitute the value of UB in this expression. See, was half Li square divided by here. Volume is the product of area and the length. Okay. Then I am going to substitute the value of L here. Now, L is nothing but self-inductance of the coil. And what is that? It is nothing but mu naught NaL. Here, half. In the place of L, I substitute value mu naught N, small n, AL. Then I is kept as such, divided by AL. Now here, this A and this A get cancelled. This way, small l and small l also get cancelled. And what remain here is nothing but this. UB is equal to half mu naught N I square. Here N is the number of turns. Small n is the number of turns per unit length of the given coil or inductor. Okay, and one more thing is known to us is that magnetic field B produced by a current carrying coil is given as mu naught N I. Okay, I am going to relate these two. So for that, what I will do, I will make certain changes to this equation. I am going to substitute this. Now before doing that, I name this one as equation number 7. Okay, now I multiply equation 7 with the mu naught and also divided by mu naught. If I do so, the value is not going to change because mu naught divided by mu naught is 1. Whenever you multiply something with 1, the value remains the same. So what I will get if I do so? I will get this. UB equals to half mu naught square N I square upon mu naught. Got it? This is what the value we obtained here. Here I done a small mistake. Here I forgot to mention this not n, it is n square. So if it is n square, then this is also n square only. Okay. Now mu naught square n square I square is equal to b square. So b square is nothing but mu naught square n square I square. So what do we obtain here is nothing but this. The final expression UB is found to be equal to half. In the place of this, I write b square divided by mu naught. This is the final expression which gives us energy density of a current carrying coil or inductor. I hope the video is useful. If you have any kind of doubt related to the topic, kindly put your question in the comment section. Thanks for watching.